Okay. Huh? What?
Between the angle gamma and the tool tip coordinate, right, in order to achieve a desired robot end
Oh,
effector.
yeah, never mind.
Just the tan inverse of 6/18.
So this shows the overall rotation, which basically
motion result in rotation and result in translation, then you have to do something very funny.
talking about singularity.
Inverse kinematics.
Inverse kinematics.
Because inverse kinematics.
The inverse kinematics.
Okay, I want you to imagine something with me. Picture this. You have your robot arm, beautiful robot arm, and you want it to move to a specific point. How do you do that? Well, that's a great question. You do that via inverse kinematics. But what is inverse kinematics? Well, I'm going to get into that. So, as you can probably guess, it's a very important part for robotics to understand this concept. I'm going to start with DH parameters. Well, my plan was to explain DH parameters, explain like transformation matrices, and go into the basics of linear algebra. But then I realized that DH parameters are useless, absolutely useless. Once I realized, I've spent countless hours, I mean, probably countable, but a lot of hours learning DH parameters, trying to understand them, because they're not that intuitive. The other method I'm going to show is a bit more graphical, so you can picture it more easily. But DH parameters are widely used. Nowadays, you just use a function in a math program and it basically does it for you. You just have to type in the parameters. I'm still going to go over DH parameters because I've worked so hard on them. It's going to be a quick part because DH parameters are useless. What the fuck? You don't need them. You set that shit up for inverse kinematics. You set all that shit up. Then you just, okay, I have my 50 matrices. I'm mad. 50 matrices. I need 2, maybe. And just move to a point where then from that point on I can solve it graphically. So why not solve it graphically from the start, which is a gazillion times more intuitive than this schmutt. And I'm not talking about icebreakers. So, like I said, for you to understand why I was so angry, I will explain them to you quickly. But the main principle of DH parameters are matrices, which is a main principle or main part of linear algebra. So I'm just going to go over them quickly. So it's time to pick the red pill. Okay, matrices. What are matrices? Well, matrices are an integral part of linear algebra. Don't get them confused with integrals. They have nothing to do with them. But what is linear algebra? So if a function, for example, is linear, it means that the input in relation to its output is in a linear relationship. That means that if I double the input, it's going to double the output. So a function, basically an instruction for a number x, and the function f takes a number x and does something with them. For example, double it. Okay, now if let's say you have 2 functions and you want to get the sum of the value of these 2 functions, your function a and function b, and function a doubles the number and function b triples the number, and you want to get the sum of those 2, what they would equal together, you can put them in a matrix. Well, it doesn't really look like a matrix yet, but it basically is. Okay, great. So we put them in a matrix, let's say G, and now the letters in G are, let's say, X and Y, but don't get them confused with the letters inside of a function, because inside of a function, these letters stand for, I don't know, some sort of number. Now, let's say we want we want the sum of a and b and the sum of m and n. For that, we would write them in a matrix under one another. So we have AB and then MN. That now looks more like a matrix than it did before. And that's basically a proper matrix. Okay, now we basically have 4 functions in our matrix. And each function basically instructs a number to do something. Maybe it tells the number to go double itself. But to do anything, we need numbers to tell what to do. We need someone to instruct for our instructions to work. For that, we also put numbers in a matrix. Isn't that intuitive? So we have our number matrix, let's say 1 and 2, and we want to multiply it with our operation matrix, which is x, y, m, n. We can say, okay, x is 3, so it will triple a number. Y is 2, it will double a number. M is 1/2, so it will half a number, and n is 1, so it will just take the number at face value. Now we want to multiply those two matrices, but how do we do that? Well, you have your matrix here and your number matrix here. You basically pour the number matrix on top. It's a very intuitive way of thinking about it. The number of numbers, a bit redundant, in the operation matrix, the number of numbers in a row in the operation matrix is called n. The number of numbers in a column in the data matrix is called p. You can only multiply two matrices if n is equal to p, because imagine you pour the data matrix on top of the operation matrix, but if there are not enough numbers, one number is just not going to get multiplied with anything. And to be honest, I've kind of been lying, since the matrices with the matrix with the operations inside is called a transformation matrix, because it transforms numbers, vectors, coordinate points, or angles, and that's basically the basis of Denavit-Hartenberg parameter. They just, if you do forward kinematics, it's going to take angles and transform them until you get a desired, or until you find out what the n coordinate is. And if you do inverse kinematic, it's going to take the coordinate points and it's going to transform them until you have the angles for each joint. That's why you have to make a transformation matrix for each joint if you're using the Denavit-Hartenberg parameter. To do that, there are first of all 4 rules to see if it even works, and then there are 4 values that you need to find out. Really quickly, they are. So really quickly, first rule is, if you have a rotary joint, they all have to move around the z-axis. So I'm just going to say the blue is the z-axis, so if you have a motor that's spinning, it has to spin around the z-axis. If you have a prismatic joint, the piston basically has to move around the z-axis, so it has to move in these directions. Second rule is that x has to be perpendicular to z in the current and in the previous frame. Means in a 90-degree angle. So here you can see that x is in a 90-degree angle in the current frame, but let's say you have a motor here and a motor here, also spins in the same direction, means that this x, which I'll just say is red, has to be in a 90-degree angle to this z and to this z, because this is the previous one and this is the current one. Or a frame is basically just a coordinate system you put on every joint. So let's say you take a motor for your industrial robot and have multiple of these motors stacked. A frame would basically be, you just think, you don't need to print these out, you just think of a coordinate frame, you put it on, and then these rules have to apply. You have a frame for every joint, for every motor. I can put this shit back now. Third rule is pretty easy. The frame has to follow the right-hand rule, which just means this finger orientation has to apply for each of the axes. And now this rule is a bit more complicated. the x of the current frame has to intersect the z of the previous frame. So if we have one frame with x here, we draw an infinite line through x, and this infinite line has to cross an infinite line that we draw through the z in the previous frame. So this would work, this would not work, because x would be like here, the infinite line would be here, and this would be here. So these lines wouldn't cross. This would work, this would work, this would work. Great. So I'm assuming that you've looked at your robot and seen and checked if all these rules apply. Now you want to actually get the parameters to make the transformation matrix. Well, there are 4 numbers that you have to find out. One of them being theta. Okay, theta. What does theta mean? Theta, in this case, means how far the x-axis is twisted from the current frame to the next frame around the z-axis. That means how strongly, how much do you have to turn around the z-axis for the x-axis to match the next x-axis. In this case, it would be 90 degrees, and from your view, that would be counterclockwise? No, clockwise. Clockwise. So it would be turning 90 degrees clockwise. Then there's alpha, which is also used to describe an angle. In this case, alpha is kind of similar to theta. This time, it's how far the z-axis, the current frame has to turn so the z-axes meet up. In this case, it twists around the common normal. Common normal most of the time is going to be the x-axis. So in this case, it would again be 90 degrees in the clockwise direction. Okay, now there's d. D is the distance between z and the common normal of the previous frame. So the common normal, as I said, most of the time is x. So it wants to know the distance between this infinite line, how far these are displaced. So in this case, it would be like a few centimeters.
Ooh, that's kind of small.
Until this red line, this blue line, not colorblind, matches the common normal of the red line. So this would be like, let's say 3 centimeters. The last value is a, which just describes how long the common normal is. So in this case, we said 3 meters is to the common normal, and the common normal would be the distance between this point, the middle point, the white point, and this middle point, the white point. And this would be about, I'd say, roughly 12 centimeters, maybe 10 centimeters, yeah. So that's A. And to reiterate, I don't see the point in using DH parameters for most use cases, so I'm not gonna go into the math, but it's still nice knowing roughly what it's going to entail. So you have your 4 values. You take these 4 values, do some funky math, a lot of cosine and sine, put them in a matrix. It's going to be a 4 by 4 matrix that the top left corner, exactly, the top left corner is going to handle rotation. It's basically a 3 by 3 matrix inside the 4 by 4 matrix that's going to handle rotation. And the top right corner, the 3 numbers next to it, are going to handle the translation. So you have your rotation and you have your translation. So you take all these 4 values, you do some funky math, put them in a transformation matrix, do that for every joint. And if you want to do forward kinematics, if you have 5 joints, you take the transformation matrix of each and every joint, you multiply them, then you do some, I think Euler had a few formulas to extract the coordinates, and then you have your coordinates for forward kinematics. Now, if you're going to use DH parameters for inverse kinematics, there are 2 ways of solving that. So of the 2 ways I'm presenting how to solve inverse kinematic, one of the ways has 2 ways to solve inverse kinematics. A bit dumb, but I guess. To solve inverse kinematics, one of them is a graphical approach and one of them is a numerical approach. And that's where my problem is, because instead you solve them graphically, it's way easier, But it's basically, you use the H parameters to get to a point where you can solve the inverse kinematics graphically.
5 hours later.
Easier, we're like, use way less complicated math. So for understanding the graphical solution, it's easy to simplify it first, to make it more intuitive. So I've made the robot, designed it, printed it. Has a lot of design flaws and it looks extremely ugly, but it works as a demonstration piece. So let's just look at it from this thing. This is 2D. And we're just gonna picture a coordinate frame. This is gonna be our X and this is gonna be our Y. And we have a point. To simplify, we're just gonna put the point as far away as possible so that our robot can barely reach it. For this, since the link lengths are 11 centimeters, as you can see here, for both of them, the maximum distance would be 22 centimeters since we have two link lengths. So to simplify even further, let's say the Y just doesn't change. It's just on 22, 0. The point is on 22, 0. So we go 22 units to the X direction and 0 units to the Y direction. As you can see, that's easy. Now, let's just imagine that instead of Y being 0, which is kind of boring, we have some other value. So Y is something and X is something, but still, so the robot has to be perfectly stretched out. Now, how do we determine this angle from the 0 position to whatever position we're in now? How do we determine this angle? Well, to do that, we just take the Y and the X. And then we use a bit of trigonometry because the Y and the X build a nice 90-degree angle here. So we can just do the tangent, Gegenkathete und die Ankathete. And you use them in the a-tan function, and then you get this angle. Perfect. We know that this angle doesn't change. Okay, what if it's something like this? How do we get the angles now? Well, this is a bit harder, but still very easy. We're just going to take the Y and the X, use Pythagorean theorem, hope I pronounced that correctly, and calculate the hypotenuse of this triangle that we just think is there. So we just picture a triangle here, calculate this distance by saying y squared plus x squared, and then take the square root of that, and then we have the hypotenuse. And then, since we know the linkage lengths, we can just use the law of cosines, which looks something like this, where we just plug in these two linkage lengths and the hypotenuse we just calculated. Take the a cos of that, and a bit more, not just the a cos of that, and then we have the angle here. And since these two are the same, we also know the angles here, because a triangle always has 180 degrees inside. So if we have this angle, we just subtract that from 180, divide that by 2, and we have these two angles. Even if this was a different length, we could still just calculate it in another way, but for our case, this is sufficient. And while thinking of this problem, I've also come up with a way that doesn't use the law of cosines. Okay, now let's say the robot doesn't have 2 linkages, but it has 3. What do we do then? But then it's also just solving graphically. Instead of solving a triangle, you solve a trapezoid, English. Even if it has 3 linkages, you can just draw a few triangles, and then it's as easy as solving the other one with a few extra steps. Now we get to the fun part. Instead of, because we are being 2D, we go 3D. It basically adds no further complexity because we can just do what we did just with one more step and one more dimension. So we take our x squared, add it to our y squared, and then add that to our z squared. And then we have our hypotenuse of that. And then we know we can immediately check if it's in the work envelope, which means the work envelope is the area that a robot can do work in. So in our case, our work envelope is 22 centimeters in every direction, because We can also spin this way. That's very loud. Since we can also spin this way. So once we've calculated that hypotenuse, I hope it's called that, we just take the x value, the y value, calculate that angle, then take the x value and the z angle, calculate that angle. Then we still just do the thing we did before with the law of cosines, because we know the length of the hypotenuse and we know the length of our linkages. So the only step that we need to do more if we have another dimension from 2D to 3D is that we need to calculate the angle of x to z. And then you have 3D space, then you have solved your inverse kinematics. It's as easy as that. And that, in contrast to the Denavit-Hartenberg parameter, which we now know I'm not that big of a fan of, is so much easier. But even though that solution is very easy, that doesn't mean I didn't run into some problems. There were a lot of dumb problems especially, but I learned a lot. So the first problem I ran into is coordinate frames. I didn't understand how you can just put a coordinate frame on a motor and just say move to that point. I felt like since the coordinate frame was basically just made up, the coordinate itself had basically no basis because it's just in the air, it doesn't have units. But then while programming, I understood how the coordinates work. Matter of fact, I should probably explain how the code works, right? Hi, let's get into it. The code is very simple. This part is all just set up. It just says, okay, the linkage length is 11 centimeters. These are the libraries we want. Then it also says, okay, these are the coordinates we have. Have fun. This function, what it does is it takes the two coordinates that we have just set up, says, okay, square these two. We don't need the hypotenuse, so we don't take the square root, because for the law of cosines, we would square the hypotenuse again, so we just leave the hypotenuse squared as it is, because we don't need the hypotenuse itself. Then we use the law of cosines, then it turns that value into degrees, because the function gives us the value in radians, and then we move on. The second function now takes x and it takes the hypotenuse, so it also takes the y coordinate, and calculates the base angle. Now the third function, and this is why I got how the coordinates and the coordinate frames work, this function just checks if a point is inside the work envelope, if our robot can even reach that point. So it firstly calculates the hypotenuse, sees, okay, is the hypotenuse even inside the range? So calculates the hypotenuse and sees if it is smaller than 2 times the linkage length. If it is inside the work envelope, it checks if the y is negative, because if the y is negative, it means that it crossed the x-axis, and we can't do that. And this is where I understood the coordinates. So we have our coordinates, we say 22 is the max because we can't go further than that, and by doing that, we basically automatically set every coordinate to our lengths, because our length is 22 centimeters. If we had, instead of 22 centimeters, 5 inches, and we would say, okay, the max is 5, that would mean every coordinate unit, every one on the x-axis would be 1 inch, and 2 would be 2 inches. It automatically maps the values to the length of your robot, which you kind of need to think about a little bit. Now is also a good time to talk about singularity. It's a concept that talks about that for every point on a coordinate system, the robot has multiple ways of getting there. If we take our robot here and say we want to reach this point, we can reach this point like this, but we can also reach this point like this. Another important thing to say is the more joints you have, the more ways to reach a point there are. So if we want to reach this point, we can do it like this, and we can do it like this, and we can do it like this, and we can do it like this. There are so many ways to reach this point, but back to me. The rest of the code is basically just unimportant. It's like running the functions that we've just written, setting up the servos, making the servos move smoothly, not trying to fix jittering and stuff. But not understanding the coordinate system wasn't the only problem. There were also problems with programming, mainly programming, because I programmed the function that didn't work. Then I tried to fix it 10 times. Then I realized that I don't need the function, so I deleted the function, and then I realized that I did need it. Functions, for people that don't know, just a part of code, a part that you can call later, so you don't have to write it every time. Then, of course, a lot of seeking help on forums, realizing that Arduino forums are very toxic. I didn't write on them. I just saw other people getting bullied. Also, multiple times I just thought, okay, while designing the robot, I thought, yeah, okay, little design flaws I can fix later in programming. While programming, hating my past self and saying, no, you're just going to redesign it. So throwing that onto my future self while programming. Past me did a lot of things future me didn't like. Then, of course, not understanding the age parameters, then finally getting them, then realizing that I've wasted 10 hours or more, probably more, hours learning the age parameters, and then being very angry because I thought, bro, are you dumb? How are you not getting this? I did get it, I just thought it was dumb, and then I finally got it, and then I realized and knew that it was dumb. Of course, probably not really. There are a lot of use cases where the age parameters are useful, but not for me. Biggest thing of all, servo jitter. Still can't fix it, still don't know what causes it. The servos have Parkinson's, and I don't know how to cure them. Neither does medicine, but I don't know how to cure them. I tried different power supply, more voltage, more amps, putting capacitors in there to smooth out the voltage, because maybe the power supply sucks a little bit. Different Arduino, better code, different servos, everything. There are no more problems. It could be in a wire, maybe 5G towers. Future me, or present me, I guess. I tried to solve servo jittering again, burned through 2 servos. That is not a pleasant smell. It doesn't smell like Chanel No. 5. So be careful, don't try to use even more amps. But they don't work. I'm blaming shitty Chinese servos because I have a lot of them and they don't have any good ones. But that being said, I talked way too much already. Now you have to try what I just taught you. If you didn't understand anything, ask me. I probably won't reply. Then try it yourself. Don't be afraid of failure. It's how you learn. Think metaphorically. Goodbye.